Hello, everyone. We're all set up here and ready to go. My name is Bunny, and I'm honored to serve as a review member of the Black Hat Asia. And thank you for joining us for unveiling the mysteries of Qualcomm's QDSP-6 JTAG, a journey into advanced theoretical reverse engineering. I'm actually very excited to hear this talk. I've been looking forward to it. It's my privilege to introduce our speaker, Alisa Esage, founder of Zero Day Engineering. Please join me in welcoming Alisa to the stage.
Hello. Thank you for introduction. For context, a few bit more words about myself. I'm an independent hacker and founder of Zero Day Engineering training and research project. And actually, my primary focus of research is binary exploitation, vulnerability research. Especially, I'm focused on browsers and hypervisors. I showed some of my exploits at Poundtown at 2021, and I also participate in vendors' bug bounty programs. So this research is kind of a little bit of a side to my normal research workflow, and it is very related to advanced cutting-edge 0 days for basebands, to put it short. So today's my topic is Qualcomm Hexagon architecture. It is a proprietary custom CPU, or so to say, DSP architecture developed by Qualcomm. And it is included in all the Snapdragon chips that are currently on the market. And Snapdragon chips, in turn, power around 30% of mobile smartphones of different brands. They kind of partner with different brands. Samsung mobile phones had Snapdragon system on chip at some point. Apple's did have it, so currently they're kind of around 30% of the mobile ecosystem runs on Snapdragon and MDM chips. And Hexagon architecture is very different from the typical mobile CPU architectures like ARM MIPS that we're familiar with. It is a very long word architecture which is optimized for parallel processing of instructions. And it is optimized for high load processing of sensor inputs and various media workflows. And most recently for neural network workflows as well. So the problem with Hexagon architecture is that it is not available for low-level debugging. And this is the problem because we need low-level debugging for binary exploit development, for serious offensive security research, as well as we need it for introspection. If a system doesn't have debugging capabilities, it means that it is very much closed off and literally anything can live with it. You can install a rootkit and you don't even have capacity to normally build some tooling to detect if there is something wrong going on in the system. But mostly for myself, my interest is for developing exploits and also finding vulnerabilities. It absolutely requires some sort of debugging capability. And for Hexagon, it just doesn't seem to exist. So for a bit of a context, here is a snapshot of a Snapdragon chip. This is a logical diagram that shows various hardware elements on the system on chip here. This is a bit from a few years ago. Unfortunately, Qualcomm stopped releasing this kind of diagrams, so I really wanted to show the more recent one, something like Snapdragon Analytics, but this is probably the latest that I could find. The most interest to us here is the processor part here. So what I want to show is that on Snapdragon's system on chip, there is not one or few ARM cores, but actually there is a whole bunch of different cores. You can see it here in the processor part. The first part here are ARM Cryo cores from a few years ago. And then there is multiple DSP. DSP stands for Digital Signal Processor. And it doesn't show here the details. I will talk a bit later. These are actually the very interesting parts. One of those DSPs runs a cellular modem, aka baseband. Another one would run some sort of sensory input from the hardware that goes then to the Android operating system and so on. So there are multiple cores, and most importantly, they run at least two distinct operating systems. So this picture that you see here, it will apply to your Android smartphone with a probability about 0.3. there is not only just the Android operating system installed and running on the ARM CPUs, which is called the HLOS, or high-level operating system, but also there is multiple DSP cores here, and they're running a completely different operating system named Real-Time OS, and here it is cured for Qualcomm SoCs. It's completely proprietary, it's real-time, and both of these operating systems are running in parallel in this typical MSM-based, Snapdragon-based smartphone. On the real-time operating system, you also have some sort of apps. They're very different from what you have on Android, like Chromium. On RTOS, you will have specialized apps that are basically more like firmware, which implement specialized functionality related to specialized peripherals. For example, there is a distinct piece of firmware which implements the cellular modem or baseband functionality. And these kind of apps are really huge, like from several 100 megabytes to several gigabytes in size. And they're written all in the Hexagon language, in the Hexagon opcodes, and they execute on the Hexagon architecture. And here I'm showing just, for example, 3 types of DSPs. They are now called separately MDSP for the mobile Hexagon core that runs the baseband, the CDSP for sensory input, and currently they also added NPU, which is the neural processing unit, just maybe about 1 year ago, which also runs on Hexagon architecture. So this is kind of our high-level context, what we're doing here. And from the offensive security perspective, one of the attack vectors come in here to the baseband, for example. And when you have some sort of vulnerability in the baseband, you literally cannot even get a crash dump from here. It's very locked down, and there is no debugging capabilities, nothing. Similarly, if you want to attack something on the NPU, it's absolutely shut off. Hexagon architecture, for a quick recap, as I said, is very unique in itself. It's custom. It doesn't look so. I know most of the popular assembly languages that currently are on the market, and Hexagon is very different from all of them. Perhaps the most prominent feature that you can notice here in the snippets of assembly is the packet instruction or packet semantic, the Kirby braces, which includes the instructions that can run in parallel on the hardware. And this is a big deal because modern processors, as you know, use various tricks to emulate or speculate parallel execution of instructions, but it is only speculative. But on Hexagon architecture, they are literally executing in parallel on the same hardware. And this is very, very important for certain types of certain types of workloads and calculations. So I'm not going to go deeper into these details. It's very interesting, and you can refer to my past talk from 5 years ago that talk a little bit more about these details of the architecture itself. So as I mentioned, Hexagon is now an NPU, and this is just a bit of marketing thing from Qualcomm that they also show very, very cool benchmarks for the NPU productivity, like 45 trillions of operations per second, which is pretty good. I'm not sure how did they test this, so this is kind of open. I just want to leave it here. And this NPU is currently also installed in a bunch of laptops for as a pilot project of unveiling the Hexagon architecture onto laptops as well. So currently Hexagon doesn't only affect the smartphones, but also it's coming into the laptops, and it already is available commercially as laptops. So when I started researching this and I found out that debugging is technically not available for hackers like myself, I started thinking, how do they actually debug the Hexagon code as developers? Because Qualcomm has its own kernel developers that build the current operating system, and they also need to test these microelectronic components, obviously, so somehow there has to be some sort of debugging functionality. It turns out that there exist a couple of ways, but they are kind of strange. So there exists a hardware product named Lauterbach 32, Trace32. It's not a debugger per se, it's a connector which connects the JTAG output on Snapdragon SoC or Dragon board to the computer, and then it goes to the Trace32 software which processes the signals. The problem with this is that it doesn't really work out of the box if you just plug it in. And the problem is not because your production-grade mobile phone is locked down, obviously. That's not a problem. But the problem is that to work with this at the hardware level, you need endorsement, partner endorsement from Qualcomm. They're consulting. They are required to set up this thing to basically to configure the whole board to enable JTAG level debugging. And this information is not public, how to do that. As a typical OEM, you would be shut off from this kind of program and you will not be able to use this hardware thing, let alone as an individual researcher for a company. So this is one problem. Regarding of software debugging, technically it doesn't exist on Hexagon, meaning that typically on operating systems we have standard debuggers which allow to debug the kernel like GDB and Windows Debugger that are available routinely and very well tested and maintained. On the Qualcomm ecosystem, this thing doesn't exist. There is no debugging per se. And as a user, as a developer, as an OEM, you are not supposed to debug it at all. So this is also, it makes it very closed off and unavailable to any sort of introspection, even for defensive purposes. There have been a bit of research in the past with DIY, people building their own software debuggers based on software vulnerability primitives, basically an exploit which is built like a software debugger. They creating a GDB server, injecting it into the baseband firmware running online through a software vulnerability primitive, and it did work, but that approach basically is very limited. Obviously, it's only tied up to a certain version, which is vulnerable. It's unstable. It doesn't allow us to debug other parts of the Hexagon firmware and so on. So, and also there is quite a bit of work here. But this approach was made, and this just goes to show how much it is important to build a debugger for commercially available architecture, that people actually are willing to invest their time to do something at this kind of engineering effort. There is also available some emulators and debuggers in the Hexagon SDK. So technically, as a high-level user, you can write some Hexagon code. I'm not sure what the use case for that. I didn't look into it. Probably you can write some specialized AI training programs that is hard optimized for Hexagon. That could be a good idea, probably. Using the Hexagon SDK, you can write the code in C or in Hexagon assembly as well. You can build it, and there is some sort of simulator or emulator available. But obviously, this is useless for actually finding vulnerabilities or exploiting vulnerabilities on the real thing, like in basebands. This shows us that there is a considerable problem, and part of this research. So I approached this research with an open mind, and I wanted to find out how debugging ecosystem is actually implemented inside of the Hexagon cores and the Hexagon SOCs, and how can we, what we can do with it, how to hack it, how to use it. As part of this research, I looked at the Trace32 software users manuals, and they are quite pessimistic. The first thing they say is that Hexagon is a secure platform and debugging is prohibited. Of course, we know that as a hacker mindset, prohibited is the figure of speech, and so is secure, meaning that here it can mean anything, and the real security or hardening is in how it is implemented, which isn't indicated here in this kind of documentation. So this kind of gives me a sign that probably these people know what they're talking about, but they don't really disclose how exactly does work. And also here it shows that some sort of different levels of debugging exist, untrusted and trusted. And this didn't really give me any information here, but it did let me find this thing that I'm disclosing today, the ISDB. While looking through Trace32 manuals and reading through the commands, I found out that they mentioned something named ISDB, especially debug registers. And this is very surprising because ISDB actually is some sort of TV broadcasting standard. And as a hacker, I know pretty much all the terminology that can appear in this kind of manuals, and ISDB wasn't one of those words. So I started looking up, and very quickly it got very mysterious because ISDB was mentioned around many open source code as related to MSM, kernel, various drivers that support the Qualcomm ecosystem, as well as in other things like Camo and LLVM. But it was mentioned kind of like they probably imported some sort of internal SDK headers or something, which basically have some macros defined, constants, but these macros are not used anywhere. Actually, I did find a couple of places where these ISDB-related macros were used in older drivers for modem on MSM. And interestingly, this code was completely removed a few years later, which also I noticed happens a lot with this ecosystem. Probably developers kind of leak a bit of internal things into public open source software, and then somebody calls them out on that and they remove it. And it happens all the time. While Googling for ISDB technology, I found nothing aside from this TV standard. One thing that I found is a handful of patents registered to Qualcomm technologies, which actually discuss this technology. And these patents became the most important source of information. Now, if you don't know, if you have never seen a patent which discloses a technology, it's not exactly the same thing as a hardware specification, for example, meaning that the purpose of the patent is somewhat opposite to the hardware technical specification. The purpose is to not disclose anything, but still make a solid claim for ownership of a specific technology, which is why these patents are very, very vague in what they're talking about, and they disclose a handful of schemes or a handful of internal details that are disconnected enough so that it's still difficult to recover the whole picture of how this thing works. So it's still kind of an effort related to reverse engineering, even though with those patent documentation. So to summarize the project that I did, it was based completely on open sources. In this particular project, I did not touch hardware. I did not try to decapsulate anything. I barely touched reverse engineering of firmware. I will notice a bit later about this. But mostly I was just looking at open sources and thinking, putting things together to disclose how the debugging is implemented on Hexagon and how this thing, ISDB, works internally. As a result, I'm disclosing today the first look at ISDB internals that would be essential for anybody who wants to enable hardware level or even software level debugging on Hexagon cores. I will not be releasing any sort of code, and I will release a recipe for trying to enable debugging with JTAG that I will talk a bit later. And still there is a lot to uncover about this. Today, because of the time limits, obviously I can only focus on the most core parts of it very quickly, so a lot has to be left aside. Fast forward to the findings. ISDB stands for the In-Silicon Debugger. It is a proprietary hardware ecosystem inside Snapdragon system on chip and anything that has Hexagon cores in it. And technically, it sits somewhat between the JTAG infrastructure and the cores. I will talk about JTAG a bit later. Here, it is important to understand that ISDB is an internal circuitry which governs everything related to debugging on Hexagon cores, meaning that both software debugging and hardware debugging, especially hardware debugging. And here, this little diagram kind of suggests that there are many ways how you can approach ISDB. For example, there are many ways to set a breakpoint here. The first two mention ISDB registers, then there is the software breakpoint implemented in Hexagon architecture, JTAG level breakpoint, and so on. And throughout this investigation, I found it seems that there is kind of a lot of different ways to work with ISDB, and it's absolutely not obvious which one of them will work out and how they're related between each other. A quick recap about JTAG. JTAG actually, it technically has nothing to do to software debugging in the context that I'm discussing it today. It's a very old technology for testing microelectronic circuits, and it's very simple. The first JTAG standard is really simple. It has typically 4 or 5 pin out, 4 or 5 pins that sometimes you can see on simple boards if they are exposed. And there is one port for data in and one port for data out. Very simple. And The thing about JTAG is it's very powerful. On the hardware level, it exposes basically everything that runs the software. It exposes all the registers of the CPU or the processing unit or any hardware. It exposes all the memory. That you can access these things directly, and there is absolutely no security around that. That is one of the reasons why basically in any research related to hardware, reverse engineering, or hardware offensive research, people start with finding out JTAG circuitry or pinouts and trying to hook into it to gain direct access to the piece of hardware as well as to software, and for example, to dump the firmware. So JTAG is kind of a very, very, very amazing thing for a hacker. And most importantly, JTAG is very commonly used to implement software debugging. If you can see that JTAG allows us, it kind of like works a little bit like in binary exploits. JTAG allows us to have several very powerful primitives like access to memory and registers of the processing unit. And with those powerful primitives, we can build a software front end, which basically will use these registers to implement software level debugging, which is how it works. And when we have a software level debugging based on JTAG, it's incredibly powerful because it allows to debug the system from the external. So with GDB or Windows Debugger, for instance, you can only debug kernel to some extent, and you always have to go outside of the system to debug the actual kernel. And then if you want to debug something like the bootloader or something that boots even before the bootloader, then this is where JTAG comes in really, really useful. Another thing to mention here is that there exist multiple JTAG pinouts, not just the 4 or 5 pin. The 10 and 20 pin pinouts for ARM were actually quite popular. ISDB primarily is communicated through ISDB registers that are listed here. ISDB registers have different functionalities, and importantly here, a handful of them is exposed to the core access supervisor mode, which is basically the kernel privileged mode of the current operating system, while majority of them are only exposed to the JTAG. Here it also shows us a distinction between trusted and untrusted access to the ISDB. But most importantly, so there are different things like you can read the status, you can enable ISDB, there is some general purpose register. Obviously, these are all undocumented. You can kind of guess what they mean, what they do based on names, but that's it. But for us, the importance is that some of them are actually accessible to the current kernel here, while others seem to be only exposed to on the hardware level. Regarding the trusted and untrusted debugging mode, trusted debugging mode is only reserved for Qualcomm kernel developers, and anybody else will go through the untrusted route, including OEMs and obviously hackers. In the untrusted mode, the set of functionality in ISDB is restricted, which is available to you, while in trusted, everything is available. Another important player here is the sysconfig register, which is also undocumented, which I found it in the programmer's reference for Qualcomm architecture. And here on the right side, you can see a snippet from the patent documentation, actually. And it kind of says that it is one of the ways to form the register, meaning that in reality, it can be a bit different. But from what I'm seeing in the firmware and how it works, that this picture is actually quite correct, and they did implement it in exactly the same way. So sysconfig register is exposed to the Hexagon programming APIs. You can use it in Hexagon programs at the privilege level, at the supervisor level only. And there are 2 bits of importance here for us. The bit ISDB core ready, which indicates to the host software if the ISDB core is currently available for debugging. And another bit is ISDB trusted, untrusted. This one is the most interesting because it literally sets whether we have full access to the ISDB functionality or only restricted access. So technically, looking at this, if you have a privileged access, then privileged execution incurred, then you can probably set a trusted mode here. And also, it says that JTAG level communication is actually done through the not necessarily through JTAG. Communication with ISDB is done through the sysconfig register, which also encodes a 40-bit packet. of data. So the next question is, how do we actually program this sysconfig register? How to set this trusted bit? Once again, I'm looking at the reference documentation for Qualcomm. So in the reference documentation, once again, I found a bit of mentions here in the older versions of programmers' reference for Hexagon developers, which mention a little bit a set of privileged registers that you can access and how to program them. Basically, you just assign a general purpose register to it to set some bits. Then you will also need to synchronize it with async instruction, which is important. And in the references, it no longer mentions much of this related to ISDB. As I said, Qualcomm seems to be just keep hardening and keep removing any mentions, any public mentions of this technology. Then, so this is an example of how it's mentioned in the reference documentation. You can use breakpoint instruction, but only if it is enabled by ISDB, and ISDB is not mentioned anywhere else. Very typical. Lastly, so that was the kind of low-level hardware/assembly perspective on ISDB, and now I found out a very interesting thing when looking through various open source codes related to MSM, which is the magic cookie. It's a specialized sequence of bytes, which stands for the letters SDBG in hex here. It's not related to core site necessarily, it's a totally different technology. And so when investigating this magic cookie, I actually found out that how it works is that Kurt kernel serves as a kind of guardian keeper for the ISDB technology. It is technically able to enable ISDB debugging, but so if you just connect to ISDB via JTAG, it will not work because this have to be enabled by Kurt kernel first, or not necessarily Kurt kernel, by a Hexagon core in supervisor mode, which is what Kurt kernel does. So how this works is that the Kurt kernel, it guard keeps this whole hardware ecosystem. It has the capability to enable or disable it, and it looks out for this magic cookie in a particular spot in the IMM, which is the shared memory on the system on chip. And once it finds this cookie, it will proceed to execute the instructions related to enabling the ISDB functionality. And it's not only the Kurt kernel, also several other Hexagon firmwares do some things related to processing of this magic cookie, which I didn't look deep into. This most probably won't be necessarily enabling of debugging per se, but something like setting up debugging for actually for this particular piece of application. So the recipe would look like this. The Kurt kernel operates ISDB. It has the capacity to enable or disable it. And it uses internally a simple flag-based mechanism to kind of control this in a very simple way, to enable or disable and maybe to do something else. And specifically, this magic cookie that I mentioned is used for the control. You have to put the magic cookie through JTAG to a specific spot in IMM. This spot will be unique to every application that you want to debug, like modem, for Kurt kernel. Some other things like PIL also seem to use it. The offset is different, but the cookie is the same. And the logic that will be executed when the software finds the cookie is also quite different. Obviously, the Kurt kernel is the main player here, which is able to enable this whole thing. And once this cookie is found in IMM by the Hexagon code, it will invoke some sort of debugging related functionality. Especially for Kurt kernel, it will enable it. Here is a snippet from the actual kurtkernel.o that I reverse engineered. You can see here it uses the cookie. It finds it in the IMM and does some tests. And then what is not shown here is that there is actually many other tests after it finds the cookie and before it actually enables the debugging. It does test for some fuses, some other spots in IMM, build time variables, flags, attestation certificates, and things like that. There's like a dozen of checks at least, which obviously you will have to bypass if you want to enable it in this way. And if all of these checks are bypassed, then it proceeds to actual enablement code here. You can see that it assigns the sysconfig register by setting a bit, probably related to enabling of the ISDB infrastructure. It does the isync instruction here. And then there is some additional logic down the line, which I am not showing here. So this is kind of how it works, how it's supposed to work. Obviously, you cannot edit this because current kernel stands upon the secure boot chain, and you only have the firmware, which you cannot technically modify unless you have a software vulnerability. So this is what you're granted. And one way how you can use it is, if you're lucky, and just attach the JDAC cable from trace32, put this cookie in the right place. If it works, it works. I guess it will only work on some sort of debugging boards, because there's some additional logic down the line. Now, if you don't have the testing device and only the release device, this code should still be there. Obviously, it's still there because this firmware reverse engineered I took out from the production device. So the code is still there, and there is a handful of ways of how you can go from here. You can either try to bypass the later checks in some way, or you can try to inject this low-level code specifically to enable ISDB in some other spot, in any spot which executes with supervisor privileges in Hexagon cores, maybe in the early stages of modem booting. So injecting this code and doing the necessary logic to enable ISDB will give you access to hardware level, JTAG level debugging on Hexagon cores. So in conclusion, to wrap it up, ISDB is the internal wiring in Qualcomm system on chips which have Hexagon cores, which sits between the JTAG and the actual cores. It adds quite a bit of layers of security to JTAG by enabling trusted and untrusted debugging, by actually guard keeping the debugging capability itself, both on the software level and on the hardware level specifically. Especially for JTAG, this is pretty interesting because usually if it is exposed, then it is exposed, and vendors don't even try to do anything about it. They kind of try to hide it somewhere. Sometimes it can be blown with fuses, but if it is exposed, then it's kind of gives full access and game over. But here, they actually try to do something that even if you have a JTAG access to a development board, and still you cannot just plug into the JTAG port and use it for debugging, because it is guard keeping by the kernel, which needs this specific logic and configuration to actually enable JTAG in the first place. This research is the first step, which today I'm disclosing this for the first time, and it gives us multiple ways to proceed further from here for both hardware level debugging and software level debugging of Hexagon cores. It kind of lays the foundation. So I will be happy to see any further developments in this direction. This wraps up my talk. If you have any questions, you can ask now.
How were you able to get the firmware images that you were looking at, looking at reverse engineering? Is that just off of JTAG?
No, it wasn't through JTAG. You can actually download it.
Oh, okay. So you just download it from them?
Yes, you can download it, and then there is some workflow related to extraction these things, but it's pretty much available.
Another question, the use of the Hexagon cores for all their NPUs and whatever they're called, is it the same core underneath and they're just putting a little bit of software on top of it, or is it actually variation in the silicon that they're using for the different uses of the Hexagon?
So there are actually multiple cores, and they are designated for different purposes. From what I've seen, they don't look like they are distinct cores with different functionality. It's probably the same kind of hardware underneath. They just designed it to execute different functionalities and different pieces of firmware. That's it.
Thanks, and good job.
If there is no question, then thank you very much for your attention. You can find my contacts here and social media if you want to connect. Thank you. Bye-bye.